Programming logic gates functions into the PLC. Describe the combinational and sequential logic gate circuits. Create PLC ladder diagrams for what? Yeah, not, and, or, NAND, NOR, exclusive OR, and exclusive NOR. Create Boolean expressions and logic gate circuits for, from two tables. We're not going to really spend a lot of time on that. We don't have a logic converter in here, so that's why that's all in red. So combination logic, this is when we use more advanced logic functions. What we do is we have 5 basic logic functions in digital. 5. We have a AND, we have an OR, we have a NAND, we have a NOR, and we have a NOT. And then what we do is we combine those into what we call combinational logic to get more functions. So all the logic you do, math circuits, latching circuits, multiplexers, all these different logic functions that you see, these are what we call combinational logic circuits. We'll look at 2 combinational logic circuits where we're going to combine some logics in this class. We'll look at exclusive ORs and exclusive NORs. So timers are made out of the 5 basic gates. Counters are made out of the 5 basic gates. Decoders are made out of the 5 basic gates. Encoders, multiplexers, demultiplexers, shift registers, and we could go on and on. Are we going to look at these? Not in this class. Next time in advanced PLCs, we'll look at shift registers. This class will get into what? We'll look at exclusive OR, exclusive NOR, timers, and counters, and that's where this class will be. 5 basic gates. So this is the 5 basic gates. What are they? These are not technically gates. They're logic functions. So when we wire these in PLCs, we're not making a AND gate. We're making an AND function. And then combinational logic, like I said, we'll look at it exclusive OR, how to wire them with relay contacts. So originally this was called relay logic, and that's what they meant. We do logic with this. Sequential logics have outputs that depends on their inputs, well as time. Synchronous, asynchronous. So anytime you hear the term synchronous, that means it's timed with some type of clock, and then asynchronous means it's untimed. We have what we call flip-flop devices, and I don't know why they're doing all this stuff. In ladder logic, we can't really, a flip-flop, I guess we can. That would be like that set reset instruction we have. That would be what we call a set reset. Sequential logic circuits, this is very impressive. These are JK flip-flop. How do they work? Well, I know. All you need to know. No. It looks impressive, doesn't it? Boolean expression. Every gate function has an equation called a Boolean expression, or called Boolean output. Boolean. We had an instructor that called it Boolean, and I don't know how he got Boolean out of Boolean. Multiple symbols represent, so we got a multiplication symbol. So we use symbols. What's a symbol?
That represents
something else. Yeah, that's what it is. So we use these symbols all the time, and we use them in math. So what symbols do we use to multiply? We got more than that. We got X. We can use that. We can use a dot, right? We can use the parentheses and put them together like that, right? We use the asterisk a lot. Why we use that? Because when we first started doing programming, we didn't have this guy right there. It was because it's not a dot, it's up in the center, right? You understand? And we didn't like to use X because we use X. It's like in math, you don't use X to indicate multiply because X is usually a variable, right? You understand? So all these we could use to represent. We could represent the AND function. So if I have a switch which one, and then I say and, which two. And that means that both of them would have to be true, right? Understand that? We use this plus symbol to represent an or. We use bubbles to represent low active, which is sometimes true. I've seen them use apostrophes to represent low active. Depends on the application, but there's several symbols we use to say. When we say low active, we mean it's true when it's low, right? So we okay. True state represented by number 1 called logic high or logic 1 Boolean output. False state represented by the number 0 called a logic low or logic 0. We've been using those terms already, right? Are we okay there? Yes, no? I know these are up on Blackboard. In course content and in the book too. That's good. Logic high represented by the on PLC, the logic high is represented by the presence of a voltage potential. Inside the PLC, where the CPU is actually at, that normally we use 5 volts, and that's been used for years. That's been a voltage that most of your digital devices and everything is designed for. All the PLC inputs, outputs can be either AC or DC, right? Our ones, we're using sourcing inputs, so and we're connected to a plus 24 volt supply. So when you press that button, it puts 24 volts inside that input. When the PLC scans that, when the program scans that, it puts a 1 in the data table, or data file for input. Logic low, represented by the absence of the voltage potential, represented by 0 volts. And this is always true. A truth table. What a truth table does is it shows us we're going to assign the inputs. Normally we assign the inputs name. And then what this would do is this would tell us every state of the input. So I've got 3 inputs, so that means we could have 8 combinations. 2 to the third, right? You understand? And then normally what we do is we just start counting. 0, 1, 2, 3, 4, 5, 6, 7. Then we come over here and we put the state of what the state of the output would go to depending on that state of that input. So what would we look at which state's cause what? True. And then we would develop an equation. So what would be my first one? By the way, another thing we use for low active, and we use this in digital a lot, is we put a bar above it. So I would come up here and I'd say A, I'd say B, we'd say not B, C. That makes sense? Y'all see where I got that? Right here. Not A, not B, C. So the bar means 0. That's what it means. So every time I put a 0 in there, I'm going to put a bar above that. Then I'm going to put this symbol right here. What does that mean? No, it don't mean ash. Not in logic. It means what? Or. Then I would come here. And what would I write? I'd write not A, B, C, or, right? Then I would say A, B, not C, or A, B, C. Then what would I probably do next? I'd see if this sucker would reduce. And a lot of the rules that you learn in algebra, we can use in Boolean. Some of them you can't, some of them you can. But we're not going to go into that because we're not doing design. But once we got a math equation for a circuit, well, a Boolean algebra equation for a circuit, or it's just like in algebra, one of the things they teach you how to do in algebra is how to do what? Reduce equations. When you reduce an equation in algebra, all you're doing is making the equation simpler. When we reduce an equation in Boolean algebra, we're making the circuit Simple. And the simpler you make the circuit, the cheaper it's going to be, right? But this would be something that an engineer would do. They would come up with these Boolean equations for a circuit, and they'd see what? They'd see if it would reduce. Sometimes they don't, sometimes they don't. But I can see this one does right off the bat. I see I can factor out A, rearrange and factor out A. Over here I can factor out A, B. And I can see right off the bat that this over here would reduce. Which they say will reduce to this. They're using a little asterisk. They say this would reduce to that, but we're not going to get into that. So we're not teaching that. All I want to do is just show you how you can do what? Develop an equation for a circuit. And then this would be symbol. So on your handout, what I gave you is the symbols from our logic. So this is a symbol that we use for a what? And. Yeah. And this is a symbol we use, and this is a symbol we use for a or. And this is a symbol we use for a not. By the way, the symbol, this is where it gets kind of confusing a little bit. Not very. What's that?
The rails like LED.
The rails are like this.
The rails like
Well, no, they're just drawing them in for the heck of it. These symbols are not drawn in. These symbols are not colored in. This is the actual symbol of an and. Now, why this guy colored them in, I don't know. That's the symbol for an and. And an and has got to have at least two inputs. But how many inputs can an and have? Yeah, two or more. Two or more. And what we'll start doing is we'll come up here and we'll actually put wings on it like that. So that looks like a top cowboy hat, right? Sheriff's hat. Ors can have multi, and these symbols are not colored in. In fact, this is the symbol. We wouldn't even draw an LED like that. This is the symbol for an LED. We draw little arrows coming out of it. And there's a lot of circuitry in here, guys. I could draw it out if you want me to, but I won't. These represent an entire circuit, right? You understand that? An entire circuit. But it does a logic. So what we find out in digital, if we integrate these in a single piece of silicon, so if one of the transistors go out on this thing, we can't replace the transistors anyway. So that's why we use a lot of these things. These are not really the symbols you'll run into PLCs. So when they decided to set up industry standards, they came up with what they call ISO symbols, and it's on that sheet. Did I put the ISO symbol there for you? That's supposed to be an and. So this is the actual ISO symbol. So odds are, even in PLCs, you're not going to see these symbols anymore. You're going to see these rectangles. Did I put the ISO symbol in? Yes, in the handout. No. No. I'll get y'all. We have a method, guys. It's called function block programming. Yeah, where we write programs using digital symbols. I think I showed y'all that on the slide yesterday, right? Not gates. So you can see the truth table. For not would be 0. If the input is 0, the output would be 1. If the input is 1, the output would be 2. This would be. Now what I'm going to do is I'm going to actually put the control device up here, which is the switch. I'm going to call that a relay. And then what I'm going to do is I'm going to come down here and I'm going to put a normally closed contact. And over here I'm going to put a light bulb. So As soon as I put power cost L1 and L2, the light's gonna come on. When I press the push button, the light's gonna do what? Go off. So in relay logic, this guy right here is that guy right there. Very simple. This is the knot. It's a knot because it's opposite of what the push button is telling me. But right now, the push button is saying turn the light off, but yet the light's on, right? So here I'm getting a 0, here I'm getting a 1. This is my control right here. This is what's determining the logic. I could use the push button down here, but understand I didn't want to use the push button because it would turn into an examine if open, examine if closed. Over here, this is not an examine if open, examine if closed. This is a normally closed contact, right? Being controlled by what? By that. Now, right now, this rung is false, but this rung is what? True. When this rung is true, this rung is false, and that's a knot. You okay? So normally when we use a normally closed contact, not an examine if open, examine if closed, a normally open contact being controlled by a relay. Sorry, this would be a knot if it's in there by itself. One contact. If I put another one over here, it's no longer a knot. If I was to come over and put another contact right there, being controlled by another device, let's say C, that is no longer a knot. That's another logic function. So a knot is only how many contacts? One, and it's got to be what? Normally closed. Are we okay? Now take a break, guys. Okay, so everybody okay how to wire a knot instruction? Just what? It's a normally closed contact, right? One normally closed contact, right? Then we get into a and the symbol's not colored in red, by the way. This is a 2-input AND, but if you look at it, got to have a minimum. To get an AND operation, you got to have at least a minimum of 2 contacts. You can have a ton of them, but you got to have at least what? 2. Okay. An AND says both inputs have to be true for the output to go true. Or let's rephrase that. Let's go output. All inputs have to be true, what? Before the output goes true. Does this make sense? So how would we hook contacts up? So I'm going to come over here. I'm just going to put an output over here. So how would the contacts have to be wired in series? Normally open, normally closed. So since we're away from the knot, we can start using it. Are we okay? Yes, no? Okay, so what we're going to do is we're going to switch over to RS Logic now. We're actually going to write the program to do a second or more than a second.
That's the second's over. You know I was going to say that. You're welcome. So here we'll drag down 3 inputs, and we'll use an examine to close. And I'm going to assign this to input 0/1. Input 0/0. Input colon 0/2. I'm going to have to keep an eye on me. I'm teaching 2 PLC classes, and Siemens does their address different. Okay, so we didn't assign any labels, and we'll go ahead and download this. In fact, what I'll probably do is do it in, and this is a what? Well, let's do logic, because we're going to use the same circuit for all our logic. Maybe a little faster with it. Okay, so we're online. Output, you know, I can see the output, but y'all can see it energized here. Y'all don't have to see it. So what's required? Yeah, 3 truths. All's the term. All. And as soon as all these go true, the output goes what? True. If any of them are false, the output goes false. Everybody okay? This is the way we would wire an AND logic using relays. They are these. I'm using inputs here because the not is the one not confusing. But it's just contacts. Normally open contacts wired in series, no matter where even if they come from an internal relay, those would be considered wired in AND. Here I'm using push button. I'm not using push button. I'm actually using switches because it just makes it so easy for me to deal with. So yeah, these are actually.
So you need 3 switches to make an output.
3, but I could use 4. I could use 5. I got to have at least what? 2. I've got 3. Input 0, input 1, input 2. Well, I'm not pushing any of them. They're switches. They do have a momentary they do have a push button. What I like about these is if you push them to the right, you get a momentary contact. So this is simulate a push button. If you put them to the left, then they latch in, which simulates just a switch.
So actually, you latch it in.
Turning three of them on.
Or more.
Or more, yeah. So notice here, I can do it. These are momentary contacts, but after a while, it would be pretty complicated. So I'm using switches I'm using them as switches instead of push buttons.
Well, I'm thinking the old circuit where you have to push 2 things to make a press.
Yeah, well, that would be an AND, and they do that a lot on manually operated press. We went down to we originally went down to Flexingate. Most of their presses were double-sided manually operated presses, and they would be loading stuff on both sides. Well, both operators had to do what? Push a button before the thing would come down. And it was what? It was a way.
Safety thing.
Yeah, safety thing. So if one guy over here on this side pushed a button, it came down. You know, I wish I could find that video. I looked for it. It was over in China, and they had the presses, and they had a bunch of people sitting between the presses. They had a gap in the presses, and they were sitting in a chair, and they were putting the stuff in, and they'd lean down, and the press would come down. I'll see if I can find that video. It was funny. I mean, it was a real. It was. Okay, guys, let's go back. Let's do what's next. What logic is next? Or logic. So, or we use it. So, and we use the term all. All of the contacts, whether they come from an internal relay coil or external or switches or whatever, all of them have to be true before the output goes So what we're going to do here is we're going to use the term any. Now notice here, 0, 0, but if B goes to a 1, the output goes to a 1. If A goes to 1, the output goes to 1. If A or B goes to 1, the output goes to 1. This would be the Boolean equation for this. So here I've got my output over here. And here's L2, here's L1. How am I going to wire inputs to give me an any? Got to have a minimum of 2, but we'll keep it as 3. And what we'd do is we would just wire the inputs in parallel. And this is switch 1, switch 2, switch, don't get that, normally open in parallel. Not just in parallel, normally open in parallel. Because you know when you say, well, I got this, it's just going to throw that old curve, right? Okay, so let's go back over to here. Let's program this in. I shouldn't have done it that way, but it's okay. So we'll take it offline. We'll come over here and we'll put a down drop, right? Highlight the run reach. I didn't want to do that. Oh, this guy's what I want. Okay. And then I'll come up here and drag this guy in here. And then I'll need another one of these guys. I'll put it right there. And then I'll drag this guy in there. And then I'll drag this guy in there. So they're hooked in parallel, even though it looks kind of the way it is. So this would be an OR. Make sure all my switches are off. So we'll come up here, we'll download this. But normally open it in parallel. AND is normally open in series. An OR is normally open in parallel. This is. An AND is normally open contacts in series. An OR is normally open contacts in parallel. Now this would be an OR logic. 2 or more. The only thing we have available is we have a NOT is the only thing. Well, we can use, we got one, I'll show y'all that. It doesn't do any logic. So, what's that? An AND is normally open contacts in parallel. 2 or more, because you can't have parallel, you can't say parallel or series without having one. 2 or more, right? An AND, did I say that right? An AND is normally open in series. Thank you. I just did that to see if y'all was paying attention to me. That's recorded, by the way. So. An OR is normally open in parallel. 2 or more. How many could you have? A lot. Not a million. You'd run out of that. It depends. Basically, it depends on how many IOs you have, right? So we're online. So I'm gonna come here. Right now. All the inputs are false, so the output is false. I'm gonna close this one, and it goes what? True, right? I'm gonna open this one and close this one. It goes true. I'm gonna open this one and close this one. It goes true. Well, let's just count. That'd be a 0, and that'd be a 1, that'd be a 2, 3, 4, 5, 6, 7. So as soon I've only got one output that causes it to when all the inputs are false, output goes false. But we won't get into that logic. So Any input is true, the output would be true.
In all the gates.
Any input true, output true, well, that would be an or. You can't say all the gates. If all the gates said the same thing, then we wouldn't have all the gates, right? You understand that? So we okay on an or. Everybody okay? Okay, so here comes the curveball. NAND. So this is a symbol for NAND. This is not the symbol for NAND. That's simulated. And they're not blue. They're just blue in the text. So that bubble means it's low active. So this means if both inputs are true, the output will be false. Or if all inputs are true, the output will be false. So here we say, okay, if all the inputs are true, then the rung will be false. Because here we're dealing with rungs, right? Okay. How are we going to make that guy? Two or more. That's right. The only one that's got a single input is the not. And then something that doesn't do any logic. Okay, guys, all the inputs, when all the inputs are true. What you mean? This means, that's a good point. So, the way we represent the symbols in Boolean algebra is if we got a bar above it, it means it's low active. If you don't have a bar above it, it means it's high active. So what we do on this one is we call, normally what we do is your inputs in Boolean algebra, in real life they're going to be long terms, but just for talking, we usually make the inputs start at A and move toward Z, and then the outputs we start at Z and move toward A. In this book, they're just using Y all the time. So the problem is that we start off with what's on the input, then I'd put A and B. And what the bar means, it means this has a low active output. So the Boolean equation for an OR, which we're going to get to next, so it'd be Y is equal to A or B with a low active output. So that's what the bar means. Above the whole expression, it means the output of the gate is low active. So this is where we'll have to move back over a little bit, but we'll look at this. So how am I going to do this? We're gonna change these over to B3 files, and we're gonna do a little. I know it's so light. Y'all see it when I do it over there. I'm like, so to demonstrate this, we're gonna have to do it. So we'll start off with when I throw power on it, the rung is gonna be true, right? You understand that? So we'll have to go back to the original diagram. Let's see. No, let me do that. Let me change. What's the B3 file? Now, these are not connected to an output, right? Can have to a 0 to 255, yeah, maximum inside a single data file. Some of your PLCs let you create additional data files. If I'd assigned symbols over here, I wouldn't have to do this. What I'm gonna do is I'm gonna move this over. And that way we can zoom in on this. Oh, thank you. I could have used 3. It's just I'd have to switch it. So check to see if we got any errors. Looks like we're okay, right? So here I'm going to use these 3 switches, and I'm going to change these. Can y'all see what I'm doing? Is everybody okay? Got to put an O, not a. So now these are all false. These are actually my inputs, guys. That's why I had to shift over. These are all false, but the output is what? True. Okay, so I'm going to come up here and I'm going to make that one true. Notice this contact open, but the rung is still what? True. Right? Understand that? We'll come up here and turn this one on. This is true, but the rung down here that I'm controlling is still true. This one's true. Oh, it didn't change over. This one's true. Now the rung went what? False. So all inputs had to be true for the rung to go what? False. So NANDs and NORs, so ANDs and ORs are what's required to make the rung go true. NANDs and NORs are going to be what's required to make the rung go false. And this is why I corrected somebody when they said contacts in parallel. ANDs are normally open in parallel, right? You understand that? An AND is normally open in series. A NAND is normally closed in parallel. I'll try. An AND is normally open contacts in series. A NAND is normally closed contacts in parallel. Yeah, they are opposites. But the problem is people's going to see, they're going to learn normally open contacts. They're going to say contacts in parallel is an OR. And we'll throw this up and somebody's going to call it an OR. Because they think contacts in parallel is OR, and it's not. Normally open is parallel, is an OR. Normally closed in parallel is a NAND. There's the curveball, right? Is that a pretty good curve? Yeah, you're right, but I said an OR. So normally open contacts in parallel is an OR. Normally closed contacts in parallel is a NAND. Yes. Normally open in series is an AND. So normally closed in series will be a.
Normally open in series.
Right. Somebody got that. Normally closed in series is going to come up being a NOR. Somebody else couple. Of course, Damien's back there. He's already had digital, so he's cheap.
Normally closed contact in parallel.
Right. What's it? A NAND, right?
I wrote it down. It just didn't come out of my mouth. The names, this can't be emphasized.
They could be, but if I move to inputs, we get in with that examine if closed, examine if open garbage. Yeah, and that's what I'm trying to stay away with. So, NAND, we're looking at a NAND right now. Parallel. NAND is normally closed in parallel. Huh? Let's write it. Let's bring up a blank thing. Let's bring up a blank PowerPoint and let's write this out so y'all can get y'all's notes right. Yeah, it's on the sheet. Look, see the sheet there? Normally open in series. OR is normally open in parallel. I'm not putting contacts, right? Are you okay? A NAND is normally closed in parallel. A NOR would be normally closed in series. And we'll see if that's true. Fixing to switch this around. This will be a lot easier. And a NOT is a single normally closed contact. One. So I have somebody come up here and I'll do this, and they'll say that's a NOT. This is not a NOT because it's got what? It's got more than one contact. Somebody in here will do that. So what logic does a single contact? What logic does that do? No, normally open. Single normally open. What logic does that do? Right? Yeah, singly normally open contact. What logic does that do? Singly normally. This is a NOT. It don't do logic. This don't do logic. This is not a 5-base single. A single contact by itself doesn't do any logic. In digital, we call them buffers. Yeah, buffer. Yeah. Doesn't do any logic. A single contact in a rung does no logic. A single normally open contact does no logic. So when it's true, the output's true. When it's false, the output's false. It doesn't do anything, right? You understand? So to do logic, we got to say all inputs have to be true, or all this, right? So that's the next thing. So let's do the NOR. So let's discard this, bring up RS logic, and we'll do our NOR. Since we've already got the normally closed contacts, should be fairly simple, right? So I'm gonna just grab this guy. I'm gonna pull it right there. I'm gonna grab this guy, pull it up, pull it right here. And then I'm gonna come up here and just highlight this little thing right there on the down here. I'm gonna hit delete, and got rid of it. Okay, so we're already through. Are we okay? So this is any. So this says now NANDs, ANDs and ORs are what's required to cause the rung to go true. NANDs and NORs is what's required to cause the rung to go false. So it looks like it's going to compile okay. I still use switch 3, sorry. Okay. So right now, all of these are false, but yet the rung is what? True. I'll come up here and turn this guy here on, my rung goes false. Turn this one on, the rung goes false. Turn this on, I'm sorry, 3 rigs. Turn this on, the rung goes false. Come in any combination, it don't make any difference. Any combination will cause the rung to go false. That is a what? NOR. It don't make any difference. Don't say all. All is any. Yeah, there you go. A lot of people want a lot of these. All is unique. It's got only one output. If it's an all, it's only got one output, right? And it's either going to be false and it's going to be true, when all the inputs are at a certain state. So that this is not an all, this is still an any. And I know you knew what you're saying, but I didn't want to get other people confused. So normally we use the term all for ands and nands, and we use the term any for ors and nors. And then that not's out there by itself. And that's our 5 basic logic gates, guys. We can start dealing with combinational logic now. But we're not going to try to come up with counters and that kind of stuff because we have counter instructions. The only one that we'll look at, the only 2 combinational logic circuits that we'll look at is exclusive ORs and exclusive NORs. We usually use the term all for ands and nands. So we say all inputs have to be true for the output to go, for the rung to go true. That's an and. If we say all the inputs are true, the rung goes false, that's a NAND. That's just a little, that helps people because now we're putting an expression up there. When we talk about ORs and NORs, we usually use the term any. For an OR, we'll say any input true, the rung would be true. For an OR, we'd say any input is true, the rung would be false. So ands or NORs are what's required to make the rung go true. Nands and NORs are what's required to make the rung go false. And I don't know anywhere a better way to teach that, guys. I don't know if anybody got any other comments or ways y'all might think of. So ands, these are normally open contacts in series. OR is normally open contacts in parallel. A NAND is normally closed contacts in parallel. And a NOR is normally closed contacts in series. A NOT is a single normally closed contact. Now, a NOT is logic. A normally open contact, a single normally open contact does no logic. Because if the input is true, the output is true. If the input is false, the output is false. It does no logic. A NOT, we say if the input is true, the output is false, right? You understand? So that's a logic. So a single normally open contact does no logic. It is not one of the 5 basic gates.
Single normally open contact.
That's exactly right.
That's what it was.
Sounds like that's exactly what I said. Okay. Not yet. Got to do exclusive ORs and exclusive NORs. We're not going to do any Karnoff maps. We're not doing any design in this class. We're not doing any reduction. That's for another class if you take that. So the last thing in here is Karnoff maps are just a method of reducing circuits. Nancy likes Karnoff maps, by the way. I like Boolean algebra. I like algebra. I like the math. So we're not going to learn Musclosky's routine, but we don't have multi-sim. I've got it on a computer over there. So what we're doing is trying to get down to the section on exclusive ORs and exclusive NORs. Does it even show it? Okay. But it is in the lab. So let's look at that. So an exclusive NOR, it's in here somewhere. I know I saw the symbol. Where's it at in y'all's book? I don't have it on my slide.
I got it on this stuff. I thought it did.
No, these are ORs. See, I'll find it in your textbook, so I don't, for some reason, it's not on these PowerPoint slides.
I don't see it, but it's on this other page. I got it right now.
We were on level 1 training We was at level 1 training over in, up in Tennessee for Siemens. And, one of the questions on the test was exclusive ORs. And I had to use an exclusive OR in one of my, so this is a common circuit.
You talking about X nor Y?
That's the way we abbreviate them. Y'all have already done one. When we did the conversion, the grayscale conversion. We don't need my classroom that way. That's even in college policy, by the way. So, exclusive OR, normally we call it XOR, abbreviation. And then we have exclusive NOR. Digital, this is the symbol. And notice we put a ghost image out on the input. An exclusive OR, these gates will only have 2 inputs. So this is not 2 or more. These guys will always have 2 inputs. Well, these are the digital symbols that we look. So R, yeah. Yeah, I know, it blends together. Now when I write, y'all notice the screen bounces. So I try to hold it on that. Right now we'll just call these A and B. And we'll instead of using PLC symbols, I'll come up and use motor control symbols. Now this is a normally open push button. And what's a push button? These are momentary contact, right? So you push them in, and you let them go. And actually, I'm going to use a switch. It makes it easier for me to hold them in. Now what I'm going to do is I'm going to come over here. So I remember the truth table for a exclusive OR. We did it. I remember that. Wait, right here. Oops. Yeah. Huh?
One more.
Yeah, this is exclusive OR. What? Just A and B. And then we'll call the output. We'll just call the output Y. What the symbol shows you is what's required on the inputs. What we get on the output when the inputs are not equal to each other. So the exclusive OR says I get a 1 when the 2 inputs are not equal. I get a 0 when the 2 inputs are equal. This guy says I get a low when the 2 inputs are not equal. That's the way this thing goes. There's always 2 inputs. So these are our comparators, guys. Using these, I can tell if the 2 inputs are equal or not equal. If they're the same or not the same. Yeah, for an exclusive OR. This says if they're not the same, I'm going to get a what? A 0. Oh, makes sense. So here, if they're not the same, the rung will be true, right? If they are the same, the rung will be false. So how are we going to wire this guy up? So right now, right now my push buttons are the same. So we're going to come up with some method where this right here will be a 0, right? I'm going to draw the same thing. I'm just going to make it a little. We'll put them in the same order. So this is an exclusive. This is an exclusive OR. So we have the same 2 inputs. Notice up here, A would be, you could swap these around, but up here, if it's normally open here, it would be normally closed down here or vice versa. So here it's what? Normally closed. So what's it down here? Up here it's normally open. So what's it down here? So I put power on this thing. The two inputs are the same. This guy's open, the run would be false.
So that's what I'm looking at, that. I'm looking at that.
What do you mean? The conclusion of what I'm trying to get done is I'm controlling this guy down here. This is the guy I'm trying to go. I don't know what you want to call it. We'll call it its main. These are the 2 inputs that are controlling main. Yeah, this is it right here. This is the guy we're trying. This is our conclusion down here, the one I'm calling main. These are the 2 inputs that are controlling main. So this relay right here, right? When it energizes, this contact would open, that contact right there would close. So right now we're starting off. So right now this is we'll call this A. We'll call this switch A. And we'll call this switch B. So over my truth table, what I'll do is I'll just change these to the switches. So right now both inputs are false. If both inputs are false, that means this contact would be normally closed, but B would be closed, but B would be what? Open. Right? You understand? Down here, A would be open and B would be closed, so there's no path to get to main. So if this is main over here, then I start off, main would be a what? Would be a 0. This rung right here would be what? False. Okay, everybody okay? So let's say I come up here and I push this button, it comes down. That's going to energize A. So this contact right here is going to open, but this contact right here is going to do what? Close. Now here we got current can come through here. Now this rung right here goes what? True. That would take care of that one right there. Right? Okay. Now we're back to this, right? So here they're the same. So I've got 0, 0, right? This shouldn't be 0, 0 down here, guys. Sorry. Somebody caught me on that, but I didn't do it. What's this supposed to be down here? So now what we're going to do is we're going to close switch B. As soon as I close switch B, then this contact is going to close, this contact's going to open. So now we got a path through here, right? The rung is true. That takes care of that. Now we got to see if this right here will make the rung go false. So I'm going to come up here. I'm going to close this. Don't raise it, Rich. False. Okay. So that means this contact is going to open, right? This contact is going to close, right? This contact is going to close, this contact is open. So notice on each one of them we have an open path, so the output will go false. So that's an exclusive OR.
So you said A.
Yeah, if I put a circle around it, it means it opened. Yeah. So as soon as I put an open there and I get an open right there, there's no path through there. So I put the bar through there indicating that B closes, right? Because that's energized. So this contact would close. A, this contact would close, but if this contact closes, what happened to that contact right there? It opened, right? And this contact gets open because that one's closed. So that gives you, now the rung goes false. Huh? Can't get a path. So that would make the rung go false. So this is the way we would wire up an exclusive OR. So how would we do an exclusive OR? So an exclusive NOR, we should end up with this. Anybody got any ideas? So we wanted to start off true, huh? What's that? So this is an exclusive NOR. So what we're doing is we're looking for something that would cause this rung to start off what? I'll start off true. Without either one of those push buttons being pressed. So we fire this thing up, we see that we have a path already where? Through here. So the run goes true. That takes care of that, right? I'll come up here and close this push button right here. That causes this contact to open. It causes this contact right here to close. What's the problem? There's no complete path, right? So that satisfies that right there. come up, close this contact right here. And that would cause this contact to open. This contact right here would close. But there's still no path, right? Okay, so that satisfies that right there. Close this push button right here, this push button right here. It causes this contact to open, this contact to open, this contact closes. This one that I erased closes, and then the run goes true. So this is an exclusive NOR. So how many inputs control an exclusive OR and exclusive NOR? 2. These are comparative. They tell us if the 2 inputs are equal or not equal. For an exclusive OR, the rung is true when the inputs are equal. It's false when the 2 inputs are either input is false.
So,
On exclusive OR.
could you bring back to the 0, 0?
Sure. That was easy. I need to draw my other contact with it. So here's 0, 0. When we say 0, 0, we mean this guy up here is false, right? And this guy over here is false. That would be the 0, 0, right? Is there a path over to the main? Yes, if these things are not energized, these normally closed would be closed. That gives us that path right there. So this run right here would be true. Go ahead and take a 2-minute break. Come back here. We'll hook these up on. We'll do it on RSLogix, and then we'll go live. All right.